All right, guys, we're going to look at the electric field at the center of an arc of charge. We'll say that arc has a length of L and a charge of capital Q, right? We're looking right here at the center, so this is our point P. What's the electric field look like due to that arc of charge? Basically, this arc of charge is like a rod that you've bent in the form of a partial circle. So I'm still going to use a 1D charge density. So that's lambda is charge per length. So it means that any little tiny length of this rod or this arc that I cut out would have the same ratio of charge to length. Okay, so I'm going to call that dq over dl. So what I'd like to do is look at each of the little tiny charges, all the little dq's that make up this charge. And then I'd like to look at symmetric charges about the x-axis, right? The x-axis here goes right through the center of the charge, right through my point P. So I want to look at the contribution from each charge that's symmetric about the x-axis. So if I look at the contribution from the bottom charge there, I get a little tiny dE, and the contribution from this top charge, I get a little tiny dE this way. And if I add those two vectors together, then I'll get something, a little bit of symmetry here that's going to make this integral a little bit easier. So let me try to pull that vector up to add those two together. Okay, and it looks like our electric field then is going to be only in the x direction. Okay, so then I want to go ahead and look at that angle theta. That angle theta is in reference to the position of this charge dq. But if I look at this electric field because of that dq, and I were to break that electric field into components, an x component and a y component, I could see then that this angle inside is also theta, right? So all that we're concerned with for each of these charges is really just the x component, because I can see that symmetric charges are going to cancel in the y direction. So I would say then, according to this right triangle, the dEx is dE times the cosine of theta. Okay. The other thing that I want to look at is as I go to different dq's, I go to other places on the arc, right? You'll notice that theta is changing. So theta is different for each and every one of the little tiny dq's. So that's something we're going to have to consider when we set up our integral. But notice also that r, the distance from each charge to the center of the circle, is just the radius of the circle. So each of those is the same. So little r is just going to be equal to the radius of the circle in every case for all the dq's. Okay, so what that's going to do for us when we go to set up our integral, we want the electric field in the x direction is equal to the sum of all the little tiny electric fields from each of the small charges, but only the x components of them from 0 to the total electric field. And then that would be equal to the contribution from each tiny charge dq all over r squared times the cosine of theta. So what we're saying here is the x component of the electric field is just dE times the cosine of theta. Great. But then we're going to go ahead and take care of any of the variables that appear here. Little r, the distance from each charge to the center or to point P, well, that's just capital R for every single dq. So our integral becomes pretty simple. E in the x direction is just the integral of k dq all over capital R squared, which is a constant, times the cosine of theta. So we want to check our two rules for integrating. Firstly, each of our variables is attached to a small factor, so the first rule is satisfied. But when I go to the second rule, is each variable attached to the correct small factor? And you notice I have a problem here because there's a theta and a dq. So what I'm going to do then is go up to this charge density, and I'm going to try to rewrite dq as a function of theta. Well, I can say that dq is lambda dl, but my problem then is I still don't have something with theta in it. So if I were to look at one of these little tiny lengths, a little chunk of this arc, right? What I'm calling DL, a really tiny portion of the total length of the arc. If I were to look again at the geometry, I've got a radius R, and it's swept out a very small arc of DL, right? And you remember from arc length formula, or the SOHR formula, that arc length is equal to theta times R. So for my little tiny arc length, it'd be some little tiny theta times the radius of the circle. So that little arc length there would just be d theta r. So I can rewrite dq as lambda r d theta. Okay. When I go ahead and substitute that back into my integral, I have integral of k lambda r cosine of theta, and I'm choosing to write that small factor at the end to get ready to integrate, and that's all over r squared. One of these r's will cancel, and it looks like I'm just taking the integral of something that is not that difficult. You're prepared, hopefully, to do an integral of cosine theta d theta. Okay, so I'm going to go ahead and bring us to a smart notebook so we can finish that integral. The first thing I need to do is make this a definite integral by putting integration bounds on that integral of cosine theta d theta. Well, for my arc, I want to integrate from below the x-axis to above the x-axis. So I would integrate from negative theta to positive theta. Okay, so let's go ahead and put those integration bounds in of negative theta to positive theta. And I know that integral of cosine is just going to be sine. The other thing that I know about cosine is that instead of going from negative theta to theta, it's probably easier to deal with one of these bounds being a 0. So the integral of cosine, because cosine is symmetric about the y-axis, right, x, y. If you integrate from negative theta to theta, the contribution from the left side is the same as the contribution from the right side. So I'm going to write that integral from negative theta to theta as 2k lambda over r, and then only integrate from 0 to theta of cosine theta d theta. Okay, so again, that's our electric field in the x direction. So Ex is 2k lambda over r times the integral of cosine. Well, integral of cosine is just sine of theta, and that's evaluated from 0 to theta. Well, sine of 0 is 0, so that term doesn't contribute. So then I can say that my electric field is just 2k lambda over r times the sine of theta. Looks great. The last thing I would do is I would substitute for that lambda. Lambda is the ratio of overall charge to length. So let's go ahead and substitute that guy in. Ex is 2kq over r times L times the sine of theta. Okay, so that's our electric field in the x direction for an arc of charge. At the center of that arc is 2kq over RL times the sine of theta.